3 I-Atlas left. The faint smear of its coma thinned its tails, unraveled into the background, and the point of light that once drew so many telescopes became just another anonymous field star, then less than that, then nothing at all. And if the story ended there, it would be clean. A visitor arrives from the dark between stars, swings through our system, and disappears again, carrying its secrets away. But comets do not leave cleanly. A comet is not a sealed object travelling through space like a polished stone. A comet is an active body, a fragile mixture of ice and dust and trapped gases. When it warms, it leaks. When it leaks, it sheds. And when it sheds, it does not only lose mass. It leaves a wake. It leaves fragments. It leaves grains. It leaves molecules that become ions and ride the solar wind. It leaves tiny patient leftovers that are too small to be dramatic, too scattered to be obvious, and yet real enough to remain sometimes for months, sometimes for years, sometimes far longer. Moving through the same solar system the comet itself has already abandoned. So the better title is not really 3 I-Atlas left. The better title is 3 I-Atlas left, but the solar system did not return instantly to the state it was in before it arrived. Something stayed behind. A trace. A residue. A thin, almost invisible signature that continues to drift through sunlight long after the nucleus is gone. And tonight that is the story. Not a story of danger and not a story of conspiracy, but a story of leftover physics. What does it mean for an interstellar comet to pass through and leave something behind? What could that something be in the real language of astronomy and space physics? How long could it last? How would it move? How would it fade? And how could we even know it was there if the thing that made it visible has already gone? To begin, we need to be very clear about the scale of left. When a comet is unbound to the Sun on a hyperbolic orbit, it is not merely leaving the inner solar system. It is leaving the solar system's gravitational embrace. It will keep moving outward past the outer planets, past the Kuiper Belt, past the region, where sunlight becomes thin and cold into a darkness, where the Sun becomes just one star among many. That departure is slow to imagine because the distances are so large. But the trajectory is simple. In principle, it is going outward and it will not come back. However, the comet is not the only thing that had a trajectory. The moment the comet began to warm, the moment it began to release gas and dust, it created a cloud around itself, its coma, and streams of material stretching behind and sometimes ahead its tails. Those particles and molecules are not locked to the nucleus forever. Once released, each one becomes its own object with its own forces acting on it, and those forces depend strongly on size. This is the first quiet trick that explains how something can stay behind when the comet leaves. The nucleus is large enough that gravity dominates its motion, but the small stuff is different. Tiny grains feel sunlight as a force. Gas molecules become electrically charged and feel magnetic fields. Some dust is pushed outward more strongly than gravity pulls it inward. Some dust is only slightly nudged. Some fragments behave almost like miniature comets of their own. When the nucleus departs, the debris does not automatically depart in the same way because it is not the same kind of object anymore. So let's step into the coma for a moment when 3 I-Atlas was still close enough to the Sun to be active and still bright enough to track easily. In the coma, the nucleus is doing something that looks gentle from far away, but is violent on the scale of the comet itself. Sunlight penetrates the surface, ice is warm and sublimate, turning directly from solid into gas. That gas expands outward at hundreds of meters per second, sometimes faster, dragging dust with it. Dust grains can be lifted from the surface like sand in a strong wind. Some grains are so small they behave like smoke. Some are larger like gritty fragments. The gas does not leave evenly. It leaves through weak spots, vents, cliffs, fractures. That creates jets which are visible as narrow streams in images. And every jet is not only a visual feature, it is momentum leaving the nucleus in a preferred direction. The nucleus recoils slightly, and that recoil can alter the orbit in tiny ways, the same way a leaking balloon can drift across a room without any engine. But the more important point for tonight is this: once dust leaves the nucleus, it is free. At the moment of release, each grain carries almost the same velocity as the nucleus. Not exactly because the gas gives it a push, but close enough that the grain begins its life in space near the comet's trajectory. If gravity were the only force, many grains would continue along paths similar to the nucleus, forming a long trail that roughly follows the comet's orbit, spreading out slowly over time. That is how meteor streams form in our solar system. Comets shed dust along their orbit, and Earth sometimes crosses that dusty path, producing meteor showers. But sunlight adds an extra force on dust, and that changes the story. Radiation pressure is the gentle push of photons. A photon has momentum. When sunlight hits a dust grain, some light is absorbed, some is reflected, some is re-emitted as heat. The net effect can push the grain away from the sun. The smaller the grain, the larger the push compared to its mass. For very small grains, radiation pressure can be strong enough that the grain's effective gravity is reduced dramatically, or even turned into a net outward acceleration. This is why a dust tail points away from the sun. Those grains are being pushed outward, and their paths curve as they move. So imagine the debris field from 3I Atlas not as one thing, but as a spectrum. Large fragments, pebble-sized or bigger, behave mostly like tiny rocks. Their motion is still dominated by gravity, and they remain near the comet's orbital path for a long time. Medium grains, like fine sand, are influenced by both gravity and sunlight, so their orbits deviate slowly and their tail geometry becomes more pronounced. Very small grains, like smoke, are pushed strongly and can be swept away into broader arcs, leaving the immediate vicinity of the comet's original orbit relatively quickly. This is the first candidate for something stayed behind a trail of larger dust and fragments that remains near the comet's path even after the nucleus has left the inner solar system. It is not a bright tail anymore. It is not a comet you can easily see. It is a faint filament of particles spread thin, quietly orbiting the sun on paths that are not exactly the same as the comets, but not unrelated either.
Tumbling slowly.
Now, because 3I Atlas is an interstellar object, there is an extra detail that makes this trail feel unusual. Most trails we think about are from comets bound to the sun comets that return again and again, reinforcing the trail over many passages. They shed dust each time thickening the stream. An interstellar comet is different. It passes once, it sheds what it sheds, and that is it. There is no second lap. So the debris it leaves behind is likely to be thinner than the famous meteor stream comets that have been feeding the same orbit for centuries. But thin does not mean nothing. Thin means hard to detect. It means subtle. So how could we detect it even in principle? One way is through scattered sunlight. Dust grains reflect and scatter sunlight, contributing to the zodiacal light, the faint glow along the plane of the solar system visible in very dark skies. But the zodiacal light is already a blend of dust from many sources. Identifying the contribution from one transient interstellar comet would be extremely difficult. Another way is through infrared emission. Dust warmed by sunlight emits infrared radiation. But again, separating a thin stream from the background is challenging. A more practical way is to keep watching the region where the trail should be and look for very faint linear structures, especially if the geometry is favourable, if the trail is seen edge-on, for example, where brightness per area increases slightly, because more dust lies along the line of sight. In some cases, trails from comets have been detected that way, but with a one-time interstellar event the odds are lower. Still, the physics is sound, dust can remain even if we cannot easily see it. But dust is not the only thing. There is a second kind of tail that comets have, and it is often less intuitive, the ion tail. The ion tail is made of gas molecules that have been ionized, stripped of electrons by sunlight or by interactions with the solar wind. Once a molecule becomes an ion, it is no longer just a neutral particle. It responds strongly to electromagnetic forces. The solar wind is a stream of charged particles flowing outward from the sun, carrying the solar magnetic field with it. In that flow, newly ionized cometary molecules can be picked up. They are accelerated and carried away, forming a tail that often points almost directly away from the sun, straighter than the dust tail. These ions do not form a stable trail in the same way dust might. They are swept into space, mixed into the solar wind. But they do something interesting while they are being picked up. They create a region of altered plasma around the comet's path. They add mass to the solar wind flow. They can generate waves in the plasma. They create what is sometimes called a cometary interaction region, essentially a disturbance where the solar wind's properties are modified by the presence of cometary ions. This brings us to a second candidate for something stayed behind, not a physical trail you could scoop up, but a temporary wake in the heliosphere, a subtle disturbance that travels outward with the solar wind after the comet is gone. Imagine a boat moving through water. It leaves a wake. The boat can be far away, but the wake continues to spread and move. In the solar system, the solar wind is the medium. The comet is the boat. The ionized gases are the interaction. The wake is carried outward by the wind. How long would such a wake last? Not long on human scales because plasma mixes and disperses, but long enough to be real, long enough to matter for a time to spacecraft that happen to pass through it, long enough to be a measurable perturbation in principle if instruments are positioned correctly. And that is the key phrase if instruments are positioned correctly. The solar system is large, spacecraft are few. It is easy for such wakes to exist without ever being directly sampled, but existence is not the same as detection. The wake can be there even if we do not taste it. Now there is another subtle remnant that can be left behind by comet activity, one that is not about dust or ions but about fragments. Comets can shed material in a more dramatic way than a steady stream of grains. They can crack, they can fragment. Pieces can separate and become independent bodies. Some fragments are large enough to continue outgassing, becoming small comets of their own. Others are inert chunks. If a fragment separates with a small relative velocity, it can remain near the comet's path. Over time, fragments spread out along the orbit like beads on a string. In bound comets, this can lead to trails of fragments that persist for a while. For an interstellar comet, fragments are still possible. And here is the important part: a fragment released near perihelion does not automatically share the same fate as the nucleus. The nucleus is unbound, yes, but a fragment's exact energy relative to the Sun depends on its velocity at the moment of release. Even a small difference can matter in principle. Most fragments will still be unbound because the comet's incoming speed is high, but some dust and small debris can end up on trajectories that are less hyperbolic even bound, especially if radiation pressure and other forces alter their effective energy. This is not guaranteed. It is not something we should claim happened in a specific confirmed way. But as a physical possibility, it is real. When you release a cloud of particles, you do not get one trajectory, you get a distribution. So another candidate for something stayed behind is a tiny population of grains that end up gravitationally bound to the Sun, joining the general dust environment of the inner solar system. Not as a visible stream you can point to, but as a slight enrichment, a few foreign grains added to a vast mixture. This is where the story becomes quietly poetic. Most material in the zodiacal dust cloud is local, generated by asteroid collisions and by bound comets. An interstellar comet passing through is like a traveller shedding fibres from its coat. Most fibres drift away. Some become trapped in the local air mixing in. If even a small fraction of 3I Atlas's dust remained bound, then in a very literal sense something from another planetary system stayed in ours. But what would that mean in practice? Probably nothing immediate. The solar system already contains dust from countless sources. A few extra grains would not change the sky. Yet the idea matters because it connects to a larger question: how much interstellar material is exchanged between star systems over the lifetime of the galaxy? We often think of star systems as isolated islands, but the galaxy is old. Encounters and ejections happen. Objects are thrown out during planet formation. Some travel, some pass through other systems, most pass unnoticed. Occasionally one is discovered and named, and occasionally some of its dust may remain. Now, if we want the title to feel true in the most grounded way, we should also admit something plain. Sometimes what stays behind is not matter. It is information. 3I Atlas left, but it left behind data, astrometric measurements, spectra, brightness curves, images of tail structures, evidence of jets, and the subtle signature of non-gravitational forces in orbit fits. Those are not metaphors. They are real artifacts stored in archives and databases available to future researchers. The object is gone, but the data remains. And data can be reinterpreted. Data can be combined with future observations of future interstellar visitors. Data can reveal patterns. In that sense, the visitor leaves behind a kind of imprint in human knowledge. This matters because interstellar objects are rare in our catalogues. Each one expands the sample size from 1 to 2 to 3, and every increase in sample size changes what questions can be asked. With one object, everything is anecdote. With a few objects, you can begin to ask whether the population is mostly comet-like, mostly asteroid-like, or something mixed. You can ask how common strong outgassing is. You can ask whether certain volatile signatures appear repeatedly. You can ask whether rotation periods cluster. You can ask whether shapes are elongated or compact. You can ask how often non-gravitational acceleration is measurable. You can ask how often the dust looks unusual. So in a calm sense, the something that stayed behind includes a change in the way our surveys operate. It includes a shift in what we expect, what we search for, how quickly we mobilize follow-up observations, and how we coordinate globally to capture a rare event before it fades. Now let's slow down again and make the physical leftovers more vivid, because the most satisfying version of this story is the one where you can picture them. Imagine the comet's nucleus as a small dark body. It is surrounded by a coma, a diffuse cloud of gas and dust. From far away you see a tail stretching behind it, and perhaps a second straighter tail. The dust tail is like a slow river of particles, each grain following a slightly different curve, because each grain has a slightly different size and received a slightly different push. The ion tail is like a luminous thread aligned with the solar wind flow. As the comet moves, it continuously replenishes these tails. The tails are not fixed objects, they are continually recreated. So when the nucleus leaves, the tail does not instantly vanish, it becomes detached. The last produced tail material continues on its own. The dust tail in particular can become a dust sheet that slowly disperses. Dust grains do not evaporate quickly, they can persist. Over time their orbits spread. Some spiral inwards slowly due to a gentle effect called Poynting-Robertson drag, where dust absorbs sunlight and re-emits it as heat, losing a little orbital energy and gradually drifting toward the sun. This process is slow for larger grains, faster for smaller ones, but still slow on human timescales. So dust can remain in the inner solar system for long periods, migrating and mixing. The ion tail is different. Ions are carried outward. They can be detected in situ if a spacecraft intersects the flow and has the right instruments. But in most cases they simply become part of the solar wind's ongoing mixture, eventually reaching the outer boundaries of the heliosphere, the bubble of solar influence and beyond. So when we say something stayed behind, we can mean a local dust trace that lingers near the original path, and we can mean a travelling plasma wake that heads outward behind the comet. Now, how would stayed behind show up in a way that makes a dramatic title feel earned? One way is through a delayed detection. The nucleus leaves, but weeks later someone notices a faint linear feature in wide-field images, or a spacecraft detects an unusual population of pickup ions at a time when models suggest a cometary source, or an unexpected dust enhancement is observed along a predicted path. These are the kinds of clues that make the story feel like a ghost. The body is gone, but the signature remains. But here we must be careful and honest. Without a specific confirmed event to point to, we cannot say that such a detection occurred. What we can say is that the physics make such remnants possible, and that space science has the tools in principle to notice them under the right circumstances. The solar system is not monitored everywhere at all times, so the truth may be that remnants existed and went undetected, in a way that makes the story even more fitting for sleep, something delicate moving through a vast medium leaving only a whisper of evidence. Now there is a deeper, more subtle stayed behind that is worth exploring, because it answers a question people often ask without realizing it. If an interstellar comet passes through, could it deliver material that becomes part of Earth's environment? Direct delivery to Earth is extremely unlikely in any meaningful amount because the comet's path and distance do not usually align with Earth closely enough, and because the debris disperses. But delivery to the solar system's dust population is plausible, and over very long times some of that dust can indeed be swept inward, and some can intersect Earth's orbit just as dust from our own comets does. The difference is quantity. One interstellar event contributes a tiny amount compared to the ongoing local sources, so this is not a story of contamination or transformation. It is a story of a faint addition, like a single grain of sand on a beach. Still, the concept is powerful because it hints at a galaxy-wide exchange of small materials. It hints at panspermia-style fantasies which we should not claim or push because evidence is not there. But it does support a calmer, more grounded concept. Star systems are not hermetically sealed. Dust and small bodies can cross. Now let's return to 3I Atlas itself in the last phase when it was still visible. As it moved outward, the comet's activity likely diminished. That is what comets do as they recede and receive less sunlight. Sublimation slows, jets weaken, the coma thins, tails fade, the object becomes more point-like. Eventually it becomes too faint for most telescopes. That fading is not instantaneous, it is gradual, and during that gradual fade the debris it has already released continues to travel, drifting away from the nucleus following its own dynamics. In the short term, the debris remains near the comet and along its trail. In the medium term, it spreads. In the long term, it becomes part of the general dust environment or is swept out. So if you stand in the present and look back at the comet's passage as a completed event, you can imagine the comet as a brushstroke. The nucleus was the tip of the brush, the tail was the paint. The brush moved through our system once and then lifted away. But the paint is still on the canvas, at least for a while. Not bright, not thick, present. Now what about the most intriguing version of the title, that something stayed behind, that is not just a diffuse cloud, but something discrete like a fragment? This is where we should separate possibility from probability. Fragmentation is common in comets but not guaranteed. Many comets survive perihelion intact. Some fragment far from the Sun. Some experience small shedding rather than dramatic splitting. If 3I Atlas fragmented in a detectable way, we would expect a clear observational record, multiple nuclei evolving coma structures, changes in brightness behavior and so on. If such evidence exists for a specific fragmenting event, it would be reported explicitly. Without that, the honest stance is fragments are physically plausible but not asserted. However, even without large fragments, microfragments and clumps are common. Dust emission is not always smooth, it can be clumpy, clumps can spread, clumps can become apparent as striations in the tail. Those clumps are not stable objects for long, they disperse. But for a time they can be real coherent structures. In that sense, something stayed behind can mean a set of structured dust features that persist temporarily after the nucleus has faded. Now there is another kind of stayed behind that is even more quietly fascinating, a change in our statistical expectations of the sky. 3I Atlas is one of the few confirmed interstellar objects. That means it influences estimated rates. It influences what surveys expect to find and how often. It influences telescope time allocation. It influences how quickly follow-up networks mobilize. It influences whether future surveys prioritize certain parts of the sky or certain detection algorithms. Those changes remain after the comet leaves. In a sense, the comet becomes a permanent member of the solar system's human story, even if it is physically gone. But we are here for the physical side, the part that feels like a ghost in space. So let's settle into one more detailed picture, the dust grain that stayed behind. Choose a grain perhaps a fraction of a millimeter across. It is large enough that radiation pressure is not overwhelming. It is released from the comet near perihelion when the comet is moving fast and outgassing strongly. The grain is pushed outward by gas perhaps at tens to hundreds of meters per second relative to the nucleus. That velocity is tiny compared to the comet's orbital speed, but it is enough to change the grain's energy slightly. The grain begins orbiting the Sun on a path similar to the comet's but not identical. Depending on the direction of its initial push, it might have slightly more or slightly less energy. It might end up on an orbit that is still hyperbolic, leaving the solar system as well. Or it might end up on a long-stretched ellipse that is bound, returning to the inner solar system long after the nucleus is gone. Even if the bound fraction is small over the enormous number of dust grains released, some could in principle remain. If bound, the grain continues orbiting. It is now part of the solar system's dust environment. It might slowly spiral inward over tens of thousands of years. It might collide with another grain and become smaller. It might be swept up by a planet's gravity. It might be destroyed. But for some time it is their matter from beyond our system now moving under our Sun's gravity. And that is a deeply quiet thought. The nucleus came and went quickly on cosmic timescales, but a grain might remain far longer, almost unnoticed. Now let's take an equally quiet thought on the plasma side. A molecule of water vapor or carbon monoxide or carbon dioxide leaves the comet. Sunlight ionizes it, or it interacts with the solar wind and becomes charged. Once charged, it is grabbed by the electromagnetic fields of the solar wind and accelerated. This creates a pickup ion population, new ions that were not part of the solar wind originally, but have been added to it. These pickup ions can generate waves, and they can alter the local plasma environment. That altered environment is carried outward. If a spacecraft were at the right place and time, it could detect a subtle increase in certain ion species or wave activity. But even if no spacecraft does the wake travels anyway, merging into the larger flow, becoming an indistinguishable part of a stream that will reach the far edges of the heliosphere years later. In that picture, something stayed behind as a moving ripple in the Sun's wind, a ripple that eventually leaves too, but on the solar wind's timetable rather than the comet's. So when we say 3I Atlas left, it is true, but the solar system is not a stage where actors step on and off, leaving nothing behind. It is a medium, it holds traces, it mixes, it remembers briefly. Now because this is a sleep-friendly story, it is worth arriving at a calm conclusion that feels satisfying without requiring a final twist. 3I Atlas left behind at minimum the material it shed while it was here, dust grains distributed across a range of sizes and forces, and gas molecules that became ions and interacted with the solar wind. The dust likely formed a faint trail that dispersed and mixed. The ions formed a wake that travelled outward. Some tiny fraction of debris could in principle become bound and remain longer, mixing into the solar system's dust population, though the extent of that depends on release conditions and is not something we should claim as confirmed without specific evidence. And beyond matter, it left behind data measurements that will outlive the event and shape how we interpret the next interstellar visitor. The comet is gone, but the solar system does not forget instantly. It forgets the way a river forgets a boat, not in a moment, but gradually as ripples flatten and eddies rejoin the current. And if you want to let the final image of tonight's story settle into your mind, make it this. Far from the sun, the nucleus of 3I Atlas is already fading into the deep black, moving toward another region of the galaxy, where it may never be seen again. But closer in inside the familiar space where planets orbit a thin scattering of dust, continues to drift each grain following its own silent curve. Some are pushed outward, some arc away, some linger. In the solar wind, a faint population of ions rides the flow like an invisible perfume carried on a breeze. Nothing dramatic, nothing threatening, just the quiet fact that even a brief visitor can leave a trace, and that trace can remain for longer than the moment of arrival. 3I Atlas left, but something stayed behind. And in a universe where most things pass without us ever noticing, the gentle wonder is not that a remnant exists. The gentle wonder is that we can imagine it at all, and that for a little while the solar system carries a few grains of another system's history drifting under our sun in the same soft light that falls tonight steady and calm as the sky remains wide enough for sleep.